Hello, my friends. Welcome to Quantum Computing with Anna. I am Anna. Welcome to my channel. Tonight's video is about something called Rutherford scattering. This was the experiment that, when Rutherford explained the results, it gave birth to the field of nuclear physics. Before Rutherford did his analysis, people didn't know there was such a thing as an atomic nucleus. By the way, you don't have to take notes from this video because if you send me an email requesting it, I'll send you the PDF with all the slides. So the story begins with atoms. Atoms were thought of as particles, tiny point-like objects. This was the basis of chemistry, which was well understood at the time the experiment we are discussing was made, about 1909. But folks had gotten curious about atoms and wondered if, when they looked at them more closely, they might have parts or different constituents that made them up. That is, they might have structure, internal structure. This motivated two individuals, Hans Geiger and Ernest Marsden, to do an experiment. They shot a beam of alpha particles at a gold foil. Now, alpha particles are basically helium atoms that have lost their electrons. These are called ions, negative ions, positive ions. They shot them at this sheet of gold foil that was very thin, only a few atoms thick. And they recorded the angular distribution of the alpha particles that came flying off. That is, they counted how many of them went nearly straight through, how many of them were deflected at a small angle, how many were deflected at a larger angle, and so on. And they put numbers to the angles, and they counted the number of particles at each angle. This was called a differential cross-section. I'm going to show you an image of the movement of the alpha particles and how they strike the gold atoms. It's a cloud chamber image from a more modern experiment, and it's taken from Wikipedia. Here it is. The alpha particle comes in from the lower right. It strikes the nucleus. This isn't gold. This is like oxygen or nitrogen, some gas. It strikes the nucleus, flies off at this angle here, indicated by the Greek letter theta. That's the scattering angle. That's the key number that Rutherford had to explain. How many particles came off at all the different possible scattering angles. Now you can also see right here a short line where the nucleus actually moved also. It's not completely stationary because it's more heavy than the alpha particle, but it's not infinitely massive. And so the alpha particle has some influence on it, and it recoils. That's that short path going towards the upper right. Now, right here in location 3, there's another collision. In a real experiment, you get multiple collisions. Now, figure 2 shows you the general scheme. You've got the beam of alpha particles, the stream of alpha particles, which I just call the beam, coming in from the left. Initially, they're traveling almost horizontal, but as they get close to the gold nucleus, the electrical forces between the nucleus and the alpha particle push on the alpha particle, deflecting it so that it goes up to the upper right. That's scattering. You can see the alpha particle on the left, the gold nucleus in the center. The orange line is the force vector, the vector of the electrical force pushing on the alpha particle when it's at that point where the orange line intersects the blue line. The green line is the scattering angle, and in this picture it's about 50 degrees. There are two ways to analyze an experiment like this and compute the scattering angle. One is to apply Newton's second law of motion, F equals ma, using the forces and solving for the position of the alpha particle all along its path, from when it comes in on the left to where it's close to the nucleus and to where it goes out. This is the approach that Rutherford took, or some people say he actually couldn't do the math and he had his graduate student do it. I don't know if that story is apocryphal or if it's actually what happened, but it is very difficult to do that approach. However, that approach, the differential equation approach, is what you find in the textbooks, and it's what you find in Wikipedia. Now there's another method, an algebraic method, that doesn't actually compute the path of the particle as it comes near the nucleus. It only looks at the behavior at large distances, the beam coming in and after it's deflected and it's gone off at a distance. This is an algebraic method. It uses high school trigonometry and vectors from freshman physics. No calculus, really. And it's much easier. This is the subject of a companion video that I've published on YouTube, and there's a link to it in the description below. Before Rutherford, people thought that the positive charge within the atom, which was responsible for exerting the force on the alpha particles, people thought that positive charge was smeared out, spread out evenly. So it wasn't expected that any of the alpha particles would be reflected backward, but actually a small percentage of them were. So regarding the history of this, centuries before that, Isaac Newton had nailed down the relationship between forces and movement in his famous 3 laws of motion. The difficulty people had at Rutherford's time was that the forces were unknown. They knew the general behavior of electrical forces, but you have to know the structure of the object that's exerting the force, and the structure of the atom was unknown. They thought the positive charge was smeared out. There was an accurate theory of the forces between charged particles. These forces are called electrostatic attraction and repulsion. They're central forces governed by an inverse square law. And what that means is that if you have 2 electrically active particles, charged particles, there's an attractive or repulsive force between them, and that force diminishes in proportion to the square of the distance between them. It either pushes the particles apart or pulls them together. This is the equation governing electrical forces between charged particles. F with the arrow above it. The arrow indicates that it's a vector. F is the force, so it's equal to the mass of the alpha particle times the acceleration of the alpha particle, the rate at which its speed and direction of movement are changing. There's a plus or minus sign, and that's there because, well, electrical charge, which measures the electrical activity of a particle, can be either positive or negative. If both particles are positively charged or they're both negatively charged, then you have a repulsion, and that's the plus sign. If one of them is positively charged and the other one is negatively charged, you have attraction. That gives you the minus sign. Now, electrical charge is a characteristic of the particle. It doesn't change. All alpha particles have the same charge, and as it turns out, all nuclei have the same charge. All nuclei of gold have the same charge. So Q1, it's measured by a number, and Q1 and Q2 are the charges. The factor of 4 pi epsilon naught in the denominator is about 9 times 10 to the 9th power. And that's there for historical reasons. It has to do with the systems of units that physicists had chosen to do their measurements in. It really doesn't have any meaning. It's just necessary to make the measurements compatible. Epsilon naught is another magic number. It's called the permittivity of free space. That phrase really has no meaning, but the number's there because of the scales at which things are measured. R stands for radius. It's the distance between the alpha particle and the gold nucleus. On the right of the equation, we have R with an inverted V above it. That's called a hat. So the symbol is called R hat. And the hat means that it's a unit vector. It has length 1, and it points from the gold nucleus to the alpha particle. So that's the orange line in the figure I showed you previously. So that's the force equation. At the risk of repeating myself, I'm going to describe figure 2 again. Here it is. The alpha particle comes in from the left, flies off towards the upper right. The orange line is that force vector between the gold nucleus and the alpha particle at the point where the orange line intersects the blue line. Our hat, which I just mentioned, is a vector that points in that direction, but it may be larger or smaller than the orange line because it has to have length 1. That's helpful in doing the math, basically. And it's really the topic for another video. There's some explanation in the companion video that's linked in the description below. The path taken by the alpha particle is a hyperbola. That's the green line in this figure. In this figure, the alpha it's rotated. The alpha particles coming in from below and scattering off towards the top, off to the left. The path of the alpha particle is the green line. Like I say, it's a hyperbola. Now, what is a hyperbola? Well, we have 2 points. They're called foci, focal points. One is on the left where the blue line and the black line intersect, right here. And one is on the right where the green line and the blue line and the black line intersect. And the deal is that for points on the hyperbola, the difference between the two, well, let me back up. The radius vector points from a focus to a point on the hyperbola. There's 2 of them, one for each focal point. And the difference between the 2 radii is the same, is constant along the hyperbola, along the alpha particle's path. And I've given the distances in this figure, and if you subtract them, you always get 4. You always get the same number. That's what makes it a hyperbola. No matter which of the 2 methods you use to calculate the scattering angle, the algebraic method or the calculus method, they both deal with something called the impact parameter. Suppose the alpha particle were electrically neutral, didn't have any charge. It would fly in a straight line from left to right, horizontally, and it would pass a certain distance from the nuclei at its point of, from the nucleus at its point of closest approach. So the red line in this figure is the path of this hypothetical electrically neutral alpha particle. The blue line The green line represents the distance of closest approach. That's called the impact parameter. And in some derivations, it's referred to as B. Periapsis is the point of closest approach, and that's used in the in the calculus method of solving the problem. And the angle in particular, the angle towards that point, which I've indicated in the figure, is the periapsis angle, or it's just called theta naught. That's the Greek letter theta with a 0 subscript. That's the angle from the beam direction to the force vector at periapsis, the vector from the nucleus to the alpha particle. And in the figure here, it's about 136 degrees. So the blue circle is the nucleus. The red line is the path that a free particle would take, and the green line is the impact parameter. And the blue line is the radius, the distance from the nucleus to the alpha particle. Here are the experimental results from a computer simulation. On the horizontal axis is a scattering angle in degrees. The point on the left at 0 indicates the particle flying straight through, not being deflected at all. The point on the right at 180 degrees represents the alpha particle being reflected directly backward. And as you can see, most of the time the alpha particle does fly straight through. But if you zoom in and look closely, you'll see that there are still some alpha particles being reflected directly backward. This is the smoking gun that indicated the existence of the atomic nucleus. This gave birth to the field of nuclear physics. So this concludes this brief introduction to Rutherford scattering, the birth of nuclear physics. If you liked it or found it helpful or useful, please click like. There will be a video soon giving the detailed path of the alpha particle, the calculus-based solution. So if you'd like to be notified of that or any of my other physics videos, enable notifications. Click on the bell icon and enable notifications. Thank you for joining me. I encourage you to subscribe to my Patreon, and I hope you have a good weekend. Thank you.